What I want to discuss today is a type of general question which is very old, very well studied, and in my opinion, surprisingly difficult. So I wouldn't have expected many of the questions I'm going to show you to be open for the length of time they were open. And, but there is, as you will see, there is some very basic questions which are very challenging and very intriguing. And I want to start with the notion of universality. So it's going to be very simple. We're given a metric space, and we'll say that it's universal if there exists some constant, okay, such that every finite metric space embeds into my given, so Y is the finite metric space, every finite metric space Y embeds into X with my Lipschitz distortion, which is this constant, independent of Y. So I'll write down the definition once and for all. So whenever I discuss, so saying embeds with distortion K, this means that you have a function f from the small metric space into the big metric space, and there is some scaling factor, S, such that in the image, the distance between any 2 points is roughly the rescaled version. So this is in X, the rescaled version up to this factor K of the distances in the smaller metric space. Okay, so being universal means that you contain everything. To show that something is not universal, you just need to find, well, we'll see that actually this constant K, there is actually, it simplifies. So this is the notion of universal. And we will see that deciding when a space is universal is actually very difficult and very subtle. But we will get to that. I want to give as a snapshot of what's going to come later is a theorem that Mendel and I proved in 2008. We call it the metric cotype dichotomy theorem. I don't expect anybody to understand what the word cotype means. We will explain all of this. So, what is finite? What do you mean finite?
That's my question.
Finitely many points.
Oh, finitely many points.
I didn't expect that. But yeah, what?
Finite in the strong sense.
In the strong sense, yes. So here is a theorem that will see where it's coming from, and immediately, I will state, in my opinion, one of the most intriguing conjectures. So this is called the metric cotype dichotomy theorem. The word cotype will be completely explained in a few minutes, but for now, it's the following statement. So I give you a metric space, and I ask you, is it universal? So actually, there's a dichotomy. So either for every epsilon, every finite metric space embeds with distortion K equals 1 plus epsilon into your metric space, or there exists a positive number alpha, depending on the geometry of the space, such that there are endpoint metric spaces whose distortion, the smallest possible distortion K, when embedded into Y, grows like a power of log. In other words, if I give you a metric space and I somehow manage to prove that every endpoint metric space embeds into it with distortion log n, the answer is, oh, that actually means every endpoint metric space embeds into it with distortion 1 plus epsilon. Okay, and the other way around, that's why, in my opinion, such questions should not be so difficult. If I give you a very specific metric space, and we will look at classical metric spaces for which we do not know the answer, whether they're universal or not, all I have to do is to find one metric space, let's say 17 points, which requires distortion at least 1.001. Okay, that's the game. It's not an asymptotic question. It's a finite obstruction and a little bit more than one. That is the only obstruction to universality. So this is the metric cotype dichotomy theorem. We'll see where this is coming from. So first of all, this answered a question posed by Aurora, Lovas, Newman, Rabani, Rabinovich, and Vempala. Really, they conjectured this phenomenon as is, except they had an additional assumption on the metric space. So this answers it in more. There is no assumption on the metric space. And there was the reason for their motivation was something in combinatorial optimization that I will not get into, but there was also some soft Ramsey theorem from the 90s of Matuszek, which motivated it, and this theorem gives a very strong quantitative version of it. But this statement as is, except there was an additional assumption, which is removed, was conjectured before by people who are not Banach space theorists or analysts that were interested in an optimization question. And the main problem, in my opinion, very intriguing, I've been wondering about it for a while, is does this alpha of x really depend on x? So maybe there is a stronger dichotomy saying that if you exhibit one metric space, 17 points, that requires distortion 1.001, then actually you can find arbitrarily large endpoint metric spaces whose distortion is at least log n to the 1 over 100. And even more so, it could very well be that alpha equals 1. That would be the sharpest possible result you can hope for, and because of a very famous theorem of Bourgain that I want to say something about it in the end as well, but the Bourgain embedding theorem from 1985 says that any endpoint metric space embeds into Hilbert space with distortion log n. And this is the truth. So log n is the best that you can hope for, and conceivably, it's true that there is actually a dichotomy. Either every metric space embeds with distortion arbitrarily close to 1, or it's as bad as possible. And we don't know this. We know a dichotomy with log n to some power, but the power that we will get, and we will see where it comes from, depends on the geometry of the metric space. Okay, so I want to start. I find this question to be extremely important, and I will also show you a suggested approach to solving it, which I cannot work out, but it's a very concrete approach in a second. But I want to discuss, so the issue of, I give you a metric space, is it universal, is very old in analysis and in geometry and in Banach space theory. There are many extremely famous and difficult theorems that have been proved over the years. I'm not going to give an entire history, but I just want to state one gorgeous gem, and actually we'll see one more, a theorem of Bourgain and Millman from 1985. And so this is just an example of a very concrete theorem, which is a major achievement about Fourier series. It says, you give me a compact abelian group, and you give me a certain subset of the dual group. Now, the notion of a Sidon set, I don't know if everybody knows, a Sidon set. So you have a group G, gamma is the dual group, and you have lambda, some subset of, so these are characters. And it's called a Sidon set if whenever, suppose it's finite for a moment. Okay, hold on. So whenever you give me gamma 1 up to gamma n in lambda, so it's not finite, but you have gamma 1 up to gamma n, you look at a linear combination of these linear functionals. So this is a continuous function on the group. And you look at its L infinity norm. You want this to be, so the only interesting direction is the lower, up to a constant, some absolute value of AI. So these guys behave as though, so these are numbers which are in absolute value 1. You would get the sum of the absolute value of AIs if they were all the sign, the complex sign of the AIs. And the theorem is that you can always find a G which gets all the signs of all of them right up to constants. Okay, this is a very classical problem in Fourier series, is to understand which subsets have this property. And there are arithmetic characterizations. So the famous theorem is of Pisier, saying that this is completely arithmetic. So an example of a classical example, I think from the beginning it was known, an example of a set of characters which satisfies this is a set of characters which has the property that whenever you, this is an abelian group, so I use additive notation. So whenever you have a linear relation like this with epsilon I, which are plus minus 1 or 0, whenever this happens, the linear relation is trivial. So this is what's called a quasi-independent set or a dissociated set. So the only solution of this implies the relation is trivial. So which means they appear here in pairs and they cancel out each other. There was nothing interesting happening. So if gamma 1 appeared with the coefficient 1, then somewhere in this sum there's going to be minus gamma 1, canceling it. And a set is a Sidon set if and only if for every finite subset of it has a further finite subset of proportional size, which is dissociated, which has this property. So this is the theorem of Pisier. It's a beautiful theorem. So this is a very old mathematics from, I think, going back to the 20s or 30s about Fourier series. And this actually, so this theorem ended a long line of work. I think Varopoulos had the initial results and Pisier and many others. And it says that if you want, so you can characterize this arithmetic property or this analytic property in terms of universality. Look at the span of the linear functionals in the continuous functions with the L infinity norm. This metric space, the closed span, this metric space is universal if and only if the set is not Sidon. So if I come and give you a set which doesn't satisfy this property, it has interesting relations, then inside the linear combinations of them, I can find absolutely every finite metric space. Okay, this is what the theorem says. Okay, so that's an example of a very classical fact about Fourier series that is related to universality. There are more. Let me now go, instead of showing theorems, let me show you a really, well, the first one I think is a really major problem on the universality question. It's going back many decades. It goes back to the work of Grothendieck. So, and it's about transportation cost spaces. So suppose you're given a metric space X and some number P. I'll always denote by P sub P the set of all Borel probability measures on X which have finite pth moments. So fix some base point in the metric space X0, and you want the integral of, you have to pth moment in terms of the distance from that X0. And the Wasserstein P metric is you look at all the couplings, all the measures on the product space, which are you're given two probability measures, mu and u, and you look at all the measures on the product space which have marginals mu and u on each of the coordinates. You look at the infimum over all the couplings, and then and the cost function is the distance with the power p. I don't know. Has everybody seen transportation cost metrics? So no. Yes, I think. So this is a very classical object. It has been studied a lot, especially in recent years, but as a metric space, it's been studied. We understand a lot about it in the isometric category, things like curvature and geodesics, etc. But in the by Lipschitz category, there is a really unbelievable wealth of open problems, which are actually much older than the recent work that has been done on this. So Bourgain's universality problem in 1986, and we will see, there are many reasons why he studied this. We'll see one of them in a few slides, is simply you look at the space of all probability measures on R2, on the plane, and you ask yourself, is this a universal space? Okay, so maybe I should give as an example. Okay, so on the real line, it's easy to prove that it is not a universal space. Okay, so that's an exercise. So measures on the real line, we know they're not, and on the plane, it's open. So very concrete, the space of all probability measures on R2, can I represent every finite metric space as measures on R2 with transportation cost metric? And what Bourgain proves is that if instead of R2, you look at an infinite dimensional space, so look at, let's say, the infinite product of 0, 1 of just the sets, the point 0, 1, the infinite cube with the Hamming distance, okay, so the L1 distance, then it is true that this is universal. So every finite metric space, if you allow yourself arbitrarily high dimensions, you can represent them as sets of measures with a transportation cost metric. We'll see why one reason why Bourgain proved this theorem. It's a very nice proof. Just a construction that puts every metric space inside there. And the open question is, do we need infinite dimensions? Now, I don't know what to believe about R2, but about R3, there is a paper which is currently a preprint on my laptop. Hopefully, it will come out soon, it says the following thing, which looks like it's going in the right direction, except that I do not know how to finish. So it says the following. So give me an p bigger than 1. And instead of R2, look at the space of all probability measures on R3. Okay? And now you give me absolutely any finite metric space XD. And you don't look at the space itself, but you raise the metric to the power 1 over p. So when p goes to 1, this is going to this tends to the original metric. But I did change the metric. This metric space can be realized as probability measures on R3. So first of all, we use 3 dimensions in the proof. Second of all, there is this annoying thing that we change the metric. Now, as p tends to 1, the Wasserstein p space tends to Wasserstein 1 in some sense. And this thing that we did to the metric, raising it to the power 1 over p, tends to the original metric space. So it looks like this is in the direction of showing that the space of all probability measures on R3 is universal, because every metric space is inside. Except that there is no compact, I cannot get the compactness to work here. When you understand the proof, it really does not, it degenerates to nothing as p tends to 1. So, but this is some sort of indication that even measures on finite dimensional objects have some universality property. Yeah.
So, Assaf, I'm sorry to interrupt the flow. If you fix a finite x, couldn't you then take a p sufficiently close to 1 so that dx to the 1 over p is very close to dx?
So even for a fixed finite x, the measures that we're forced to use are forced to have support further and further, as p tends to 1, further away from the origin. So they're like disappearing to infinity.
Yeah, no, but don't take the limit. Fix the x. Oh, I'm sorry, I see.
Yeah.
I see.
Okay, so somehow they're disappearing in the cracks between your fingers, and then you get nothing. So I do not know. I really don't think that this method addresses the p equals 1 case, which is important for many reasons. But it's some sort of indication that you have some sort of universality properties, but we are struggling. And this is also R3, not R2, but if you manage to prove universality for the probability measures on R10, it would be a very nice achievement. I mean, a major achievement. Many people tried. Now, the reason I'm stating this theorem, other than to show that it's hard to decide universality, is, so first of all, this theorem is sharp. You have to raise the metrics to the power 1 over p. So this we can show. If you give me any number bigger than 1 over p, then I can construct endpoint metric spaces such that if you raise the metric to the power alpha, alpha is a little bigger than 1 over p, then any embedding of them into the transportation cost space with power p goes to infinity, like log n to alpha minus 1 over p, which is a positive number. So this ends at 1 over p. We do have an example showing that this theorem is sharp. And I have good reason to conjecture, but I stated as a question that I believe that there is a good chance that here's a very concrete question in embedding theory. Is it true that every endpoint metric space, and this is just the case of alpha equals 1 of the sharpness statement. So is it true that for every endpoint metric space, you can realize it as measures on R3 with the Wasserstein p metric, but with distortion log n to the 1 minus 1 over p. That would make, that's the case alpha equals 1 of the example. If that were true, that would finish the metric dichotomy problem. And I do believe this is a candidate counterexample, or I don't know what you expect in the dichotomy problem, but it would mean that the space of probability measures on R3 with the Wasserstein p metric, the true asymptotics, every endpoint metric space embeds into it with distortion log n to the 1 minus 1 over p, and that's the truth. As p tends to 1, you get arbitrarily small powers of log. So if you remember in the cotype dichotomy problem, we said that it has to grow like log n to some alpha, and I asked maybe alpha equals 1 or alpha equals a half. So I believe that a good place to look for counterexamples is the measures, probability measures on this room in R3 with the Wasserstein p metric, but there has to be an embedding theorem about a general endpoint metric space. So here is a very clean question about finite metric spaces and measures on R3, which would solve the cotype dichotomy problem, but I think it's independently interesting. So that's just one example of how difficult it is to decide universality. Let me show you another one. And that's, again, I should say that this universality problem for Wasserstein 1 goes back to the work of Grothendieck. He actually announced a proof of a certain weaker result, announced it without proof in a certain paper, and it took a while to find the proof. So he claimed to have proved, he studied this question actually for reasons that we will see later, but there was some sort of controversy around part of his work in this respect. But let's go back to another thing. There is this notion of a projective tensor product. So if you have two normed spaces, x and y, then we look at their linear, their algebraic tensor product, x tensor y, and we put a norm on it, which is given here by the formula. So I take a vector z and I represent it as a sum of simple tensors. For every such representation, look at the sum of the products of their length, and I take the infimum. So this is, if x and y happen to be finite dimensional, this is the same as saying, look at the tensor product, look at the simple tensors x tensor y, where x and y range over all unit vectors, and take the convex hull, that's going to be the unit ball of the projective tensor product. Okay, this is really a projective object in the appropriate category. There is also an injective tensor product. This is all very well understood. A very important construction. So here's an easy exercise. Both are easy exercises. If you take an L1 space on any measure and you look at the projective tensor product with any Banach space, you just get the vector value of the L1 space. All the measures, all the functions taking value in x with the norm is the integral of the norm of the function. The second example is the projective tensor product of Hilbert space with itself. That's exactly the shot and trace class. So this is the space of all compact operators in Hilbert space, and the norm is the sum of the singular values. Okay, so the trace of t star t, the absolute value of the operator. Again, a nice exercise in linear algebra to prove this. So this is a lot of classical spaces come from projective tensor products, and for many years, people have been interested what properties are preserved under projective tensor products. So today I'm just focusing on universality, but this is a big area. So there are many geometric properties that you can ask if x has them and y has them, does also the tensor product have them, inherit them. So there is actually a remarkable theorem of Pisier. It's an absolutely beautiful construction. He proved that there are two Banach spaces, x and y. Both are not universal. So they both do not contain everything. Yet their tensor product does contain everything. And these are really substantial. This is a really substantial construction. So he constructs very cleverly a Banach space Z, such that if you take the projective tensor product with L1 over H1, so I look at, this is, L1 will be L1 of the circle, and H1 is just going to be the closed span of e to the I n theta, but when n is non-negative. So, so this is exactly the limit values on the circle of the Hardy space of analytic functions in the interior of the circle. So that's a nice closed subspace of L1. L1 over H1, the fact that it's not universal is in a very famous and difficult theorem of Bourgain. So this is a very substantial theorem in analysis. He proved this is a corollary. He proved something else. This is one of the main corollaries of it. So L1 over H1 is not a universal space. Pisier comes up with a companion space, which also is comes from Hardy spaces. So there's some complex analysis behind it, so that if you tensorize these two guys, all of a sudden you get a universal space. So this is a nice construction, very substantial, both ingredients, the two spaces that come in, the fact that they're not universal, this L1 over H1 result is a very beautiful result, a really substantial result. So, so there was an old question of Distel, Fourier, and Swart, well, probably asked long before. The first place I found it in print is in this survey of theirs from 2001. And they asked, what happens if you just tensorize with an LP space? So you take a Banach space X, and you tensorize it within LP space, if X itself was not universal, does the tensor product also inherit this property? Now, the reason they ask this is because there was this industry, so there are many properties. There were the Nicodim property. There are many properties of Banach spaces, which Pisier, actually Pisier and Bourgain, and even Pisier-Bourgain in joint paper, I think their only joint paper, always found examples of spaces such that both of them have the property, but their tensor product fails it. And then somebody else came along and said, but if one of them is an LP space, this cannot happen. Okay, so it seemed that you can do crazy constructions, but if one of the spaces is in an LP space, then a lot of properties are preserved under tensor products. So these are, again, two substantial theorems. The shut and trace class is not universal. That's a fun exercise. Not an exercise. It's a real theorem of Tomczak-Jaegerman in 1974. It reduces to a very nice inequality on matrices. And Pisier extended this in 92 to say that if P and Q are bigger than 2, then LP tensor LQ is also not universal. But recently, Briette and myself and Regev managed to prove that this conjecture, we can get the same sort of phenomenon as in Pisier's theorem, but when one of the spaces is even Hilbert space. So I can give you a Banach space that is not universal, but if you take its tensor product with Hilbert space, all of a sudden everything fits inside. Okay? It contains all finite metric spaces. And then you can do all kinds of funny looking things. You can find a Banach space Y, such that Y tensor Y is not universal, but 3 times is universal. Okay, so, and these spaces are not crazy. So Y can be L3, and X can be L4 tensor L4 in all of these things. Okay, so we answered this question, but this required substantial amount of work. This is a topic of a completely separate talk, maybe in the future. But this is a fun combination of vector-valued Fourier analysis and actually really substantial results from coding theory, the theory of locally decodable codes. We use them to do this. So again, I want to highlight open questions about universality. Here are very concrete questions. L2 tensor L1.5. There's very concrete space. I can give a formula for the norm, and I cannot decide, nobody can decide, whether there exists one metric space. All we need is to find one, let's say, with 100 points, 23 points, that requires distortion at least 1.01 in this space. That's all I ask, and we cannot decide this. And the same goes for, if you want, Hilbert space with itself 3 times. And this is both questions have been popularized by Pisier. But this and the transportation cost spaces, these are very concrete classical spaces for which, even though all I have to do is produce one example of a finite metric space which doesn't embed isometrically, I cannot decide this. And these are very old questions. Okay, so universality is a big deal. And now I want to show how this relates to what we discussed yesterday without referring to it. What does the word cotype belong here, and how does this relate to analysis? So, okay, so this is something that we discussed yesterday, but I will remind. So we did this exercise yesterday, but for the reverse inequalities. But let's just look at the inequalities as they're written here. So this is a very easy exercise. So if, again, just uses the fact that the norm is convex. In any Banach space, if you give me an n tuple of vectors in the Banach space, and you sum them up but for each one of them you flip a coin. If you add xi or xi in the opposite direction, compute the length of this vector, take expectation, that's always at least the average, the expectations, the second moment, that's always at least the average of the squared lengths of the vectors. Just convex, this is nothing more than the convexity of the norm. True in any Banach space. So just as we did yesterday, you want to ask, can I improve over this asymptotically? So can I get in this lower bound a constant times n to some positive power? So we'll say that the Banach space is Rademacher type Q if for any n tuple of vectors, the same inequality that's always true actually gets improved. You get an additional factor going to infinity, an n to the 1 over q. And so for those who weren't here yesterday, we did the same thing happened for the notion of Rademacher type, except the inequalities were reversed. And the trivial inequality was I'm writing down the definition of Rademacher type, but the trivial inequality was the case p equals 1. So with n, this was just a triangle inequality. And we want an asymptotic improvement over the triangle inequality. That's the notion of type. And cotype is, again, an asymptotic improvement over convexity of the norm. So this is a geometric property of a Banach space. As yesterday, it's a definition star, so purists, including me, don't use this definition in textbooks. There is an intermediate definition which implies it, a slightly stronger property. And the difference between the property I wrote here and the actual definition will not appear in any theorem that I'm going to state in this talk. So there is there's a nuance here which is irrelevant to anything I'm going to state. So let's take this as a definition. So is the definition clear? So the relation to universality in the linear world, and this is going back to the 70s, is that let's see what is the obstruction to the inequality up there. The second inequality, the definition. So suppose I can give you n vectors in my Banach space, which are equivalent to the L infinity unit basis, the standard basis of L infinity, which just means that if I sum them up with coefficients in R, some ai xi, up to universal constant, this is the L infinity norm of the vector A, the maximum of absolute value of xi. Then if I try to write down the inequality, so the middle term here is the inequality I was shooting for. So if I sum the vectors with random directions, I get a vector of constant length because it's the maximum of, up to constants, it's the maximum of ones. While, oh yeah, I should have said there, and they're unit vectors. So up there, these are, x1 up to xn are unit vectors, and they said oh, actually it follows from, yeah. So because they have constant norm that follows from the assumption, the inequality I'm shooting for just tells me that n to the 1 over q is at most 1, so q is infinity, so it's trivial. Okay, so whenever I have an L infinity inside the Banach space, I'm done. I cannot get an improvement over this convexity. I cannot get this cotype. And this is similar to the phenomenon we saw yesterday. Bourgain-Pisier proved in 75, this is a deep, this is a simple case of a deep theorem that I will, a simpler case of a deep theorem that I might mention later. It's called the Bourgain-Pisier theorem, and it says that the only way to get an asymptotic improvement over the trivial inequality, the only way to not have an asymptotic improvement over the trivial inequality is the way that I wrote here, is because L infinity exists inside. Okay, so L infinity is a universal object. So in other words, for a Banach space, either the trivial inequality cannot be improved, or it's universal. Okay, and or it's not universal. And when it's not universal, all of a sudden you get an asymptotic improvement. You get this n to some positive power in the inequality. So this is of massive importance. So this controls things like cotype is an invariant that appears in many, many examples. And in the linear world, we understand that this is a concrete inequality, a concrete metric invariant, which controls universality. And as we did yesterday, so Ribe's theorem, so this is a theorem I stated yesterday, said that if you have two Banach spaces which are uniformly homeomorphic to each other, there is a homeomorphism between them which is uniformly continuous in both directions, it implies in particular that if one has cotype Q, then also the other. So it was a more general theorem, but that's what it implied. And the question is, can we define the notion of cotype for a metric space? So I'm writing down we worked out yesterday the definition of type for a metric space. So this was I'm just repeating something as we did yesterday. A metric space is metric type P if whenever you take a function from the Hamming cube into the metric space, which is just 2 to the n points indexed by the Hamming cube, the expected length of a diagonal is at most n to the 1 over p times this average of lengths of edges, squares of length of edges. Okay, so this is, and we worked this out yesterday, and we saw that this has all kinds of nice implications. For metric spaces, the link to Banach spaces was that in Banach spaces, when f happens to be a linear function, it's written there, f of epsilon is some epsilon I xi, this is the linear definition. It just becomes the linear definition. And now we do this huge leap of faith, and we say maybe it's true for general functions, not only for linear functions. So this was the exercise, is a step in the Ribe program that we did yesterday. And in the linear world, we know that type and cotype are just reversals of the same inequality. But now we have an issue. So it's been open for many years how to define cotype for a metric space. And that was actually a big problem because in essence, we had half a theory for a long time. And a point that I want to make, there are many reasons why this is more subtle. But one of the reasons is that you cannot simply reverse inequalities in the metric world, unlike in the Banach space world. Okay, so what do I mean by this? This is the type inequality that we discussed yesterday, and it was a very meaningful inequality even for metric spaces. So now let's reverse it. This is the naive thing to do. So we flip the direction of the inequality, and I just change P to Q for cotype. Okay, so that's what we hope, one would guess would be the definition of cotype for a metric space. If the reasoning that we did yesterday works here, this is complete analogy, just flipping the inequality and calling PQ. So this is the same, that just square everything. It's the same as the expected diagonal squared is at least this function of n times the sum over I, and then the expected length of an edge. So the distance from f of epsilon and f of a vector, a vertex of the cube in which I changed the sign only of the ith coordinate. And this is fine, and this is cotype for linear functions. There's no problem with this. But we have to deal with, in the linear world, with nonlinear functions. And if your metric space contains at least 2 points, let's call them A and B, then let's look at a random function which chooses at every vertex of the cube epsilon, chooses either A or B with probability 1/2. Okay, so this is what's written here. For every epsilon, we'll let f of epsilon be with probability 1/2. A with probability 1/2. The A looks like a part of the sentence. A with probability 1/2 and B with probability 1/2. Okay, so if this inequality were true, and this is just 2 points, it's not an interesting metric space, so we can write it for this f and now take expectation over the random f. And over the random f, the expectation, the distance from f of epsilon and f of minus epsilon is just the distance from A to B times 1/2. And the same goes for the edges. So the inequality becomes what's written here, which forces Q to be infinity. So there is no improvement over the triangle inequality in any metric space unless it's a singleton. So we cannot take what we did before, which wasn't naive, it required work, but we cannot just do the same thing and reverse inequalities. That's one. There are more reasons why a certain form of an inequality cannot be the definition of cotype. So this was a huge mystery. It was when I was a graduate student, this was kind of a reason that held back the Ribe program, because we really did not, we had half a theory and somehow half a dictionary, and we couldn't state many conjectures even. So in particular, this theorem about the Wasserstein-1 distance, the transportation cost distance in Bourgain, the reason he proved that the implication, the reason that he proved that this was a universal was that before that, Bill Johnson proposed a definition of cotype for a metric space which involved transportation cost metrics. And the fact that the infinite product, the infinite cube, fails to be universal, is universal, destroyed the entire plan. It destroyed the potential definition within the Ribe program for metric cotype. So I will not tell you what the potential definition was because it's all broke down, but Bourgain was actually, that was his goal when he proved this theorem. So now let me show you a definition that, it's not 2010, it's 2008. The year is wrong, but let me show you the definition that Mendel and I came up with. So it will look a little complicated, but it's actually very simple, and we'll write it in a simpler way in a second. So it's the following statement. So you're given a metric space. It's not a Banach space, it's a metric space. And we'll say that it has metric cotype Q if whenever you give me an integer n, I can find an integer m such that now instead of cubes, I look at the integer grid, the discrete torus, z2m. I want it to be even for some technical reason, z2m to the n. I take an arbitrary mapping from this into the metric space, which is nothing more than, right, 2m to the n points, indexed by the torus. And I want that for every such function, the following inequality holds true. Take a random point u in the torus. Take a random L infinity edge. So if this is the torus, then the L infinity edges are these edges. Right? So these are adding a vector of +1, -1, or 0 to the vector. So I look at the L infinity edges. I take the expectation, I multiply it by m, and this has to be at least n to the 1 over q times what? Times the displacement of the function f. So here is f. If this is f of u, I add m. M is half the z2m is my torus. So I add m. So this is u, and this is u plus m ej. I add m in one of the coordinate directions. I look at what is the distance in the metric space, and I take expectation. So this looks crazy. So first of all, I just expelled out the expectations, but the inequality looks like this. Expectation means over random epsilon and random u. And the idea is that in the link between this and cotype is that in Banach spaces we can rescale things. So in the case of Banach spaces, if I take f of u to be some uj xj, then if you look up there, so what is u plus epsilon minus f of u? It's just some epsilon I xi, if it's linear. So the top row is just the right-hand side of the inequality. And if I add u plus mej and I subtract f of u, but f is some uj xj, then I just get xj times m, and m cancels from both sides. Okay, so the rescaling, there was once an adding a horizontal displacement inside f. That's in the bottom term, and there was an m multiplying the entire expectation on the top term. For linear functions, these m cancels. Okay. And it just becomes cotype. So of course, I said it's linear star. UJs are elements in the torus, so you really have to look at the real function f you have to look at is some e to the pi I uj over m. But so you respect the wraparound, but never mind that. And just as before, if you do the same exercise, if your metric space contains 2 points and you take random every vertex of the torus you assign to it one of these 2 points at random, now it just forces m to be at least n to the 1 over q. Okay, so that's not a big deal. If m is big enough, I do not get the same contradiction that I had before for these random functions, which are really nonlinear objects. And we will see very soon that spaces in which we can get n to the 1 over q play an important role in applications to coarse geometry and quasi-symmetric embeddings. We'll get to this. So, but remember that m has to be, unless your metric space is a singleton, m has to be large. How large? N to the 1 over q. Okay, so this looks, it's all legitimate. It's obviously an extension of linear cotype to metric spaces. But this is a completion of the Ribe program because of this is the main theorem, is that a Banach space has Rademacher cotype Q if and only if it has metric type Q. So this was an inequality involving only distances, which is equivalent to the linear inequality. So this is exactly what we wanted to do in making Ribe's theorem concrete. So this finishes the Ribe program. As I said, the Ribe program, first you have to reformulate things in terms of metric spaces, but then you have to show that it's good for something, and we'll see what it's good for. I just want to say that we also know how to get the best possible m, and now there is a technicality, which I do not believe is there, and that's a major open problem. If your Banach space happens to have type bigger than 1, then I can get that it satisfies the metric cotype inequality with the best possible M, and that will be very important later. Okay. Now, so this was yesterday. We discussed this at length. I do not want to focus on it today, but the main issue of this is in these types of inequalities is that what the information that you have is that your Banach space is cotype Q. So it satisfies the inequality up there for linear functions. And from this, you need to deduce that it satisfies it for every function whatsoever. The only thing at your disposal is the inequality for linear functions. And now you have to deduce that it holds for all functions. So again, this is an issue in Fourier analysis, just like we described last time. And I want to say the main open problem, which is when we'll explain the applications, you will see why you want to know it. Do we need this additional assumption of type bigger than 1? Is it always true that we can get the best possible M for Banach spaces? So we do not know this. We're actually way off. Our original proof in 208 was off by a factor of n squared. And we worked hard to shave a little bit off of that. But we also managed to show that in a very strong sense, in a very strong generalization of our approach, this is something called the smoothing and approximation scheme, anything using the approach that we came up with will never hit the mark. So I can prove that a really new idea is needed to get the sharp value of M. The way we got M to be the correct value when the space is type bigger than 1 uses actually more sophisticated Fourier analysis, which is simply false in general. So we use it in a very, very strong way. So this is the situation. So that's a major open problem, very concrete. And I would really like to know the answer. Here is one reason I would like to know the answer. There are several, but this is one of them. So it's actually saying that suppose you have a metric space and it embeds. There is a uniform homeomorphism between your metric space into you want to prove that there is no uniform homeomorphism between your metric space and a subset of the other metric space. So you need to find some sort of invariant. And this is essentially one of the two, I think, or three invariants that are known. So cotype, it's not obvious immediately, but you can, by a computation, you can see that it's an invariant. So if you give me any metric space X, which happens to satisfy the metric cotype inequality, but with the best possible M, which we do know for a wide class of Banach spaces, then if you have a Banach space that embeds that is uniformly homeomorphic to a subset of X, then it inherits the cotype. So cotype is an invariant under this weak notion of embedding. And one of the corollaries that we could use is to classify when LP is uniformly homomorphic to a subset of LQ. So in this very classical sense, this was actually a really old question. It was asked by Enflo in the 70s. And we couldn't decide when. So when is LP uniformly homeomorphic to a subset of LQ? The answer is if and only if either P is less than Q or they're both less than 2. Okay, and this comes when you start computing the cotype of these spaces. And you just check, you have this number is an obstruction, and it turns out to be the only obstruction. So it's invariant, and it finishes this question of classifying when LP is uniformly homeomorphic to a subset of LQ. There are other notions. There is a notion of coarse embedding, which I will not get to today. This settles the same question for coarse embeddings. And then, actually, after we published this, I heard that there's people in the quasi-symmetric community had this question since 1996. This is one of the main questions that Vaisala asked in a famous open problem list. And the same method does this. So I won't tell you what quasi-symmetric embeddings are unless you ask in the end. But it's a notion that appears a lot in geometry. Also, coarse embeddings appears a lot in geometry. And these are very weak notions of embeddings. And cotype serves as an invariant. It can be used to show that something doesn't embed in a very weak sense into something else. Okay, now the Minerva-Lectures theorem. So here is now a statement. Again, it started from Banach spaces. In the 1970s, we understood this. I quoted the theorem before. And our notion is the right notion in the sense that now we have a theorem about metric spaces. This has absolutely nothing to do with Banach spaces, except that that's how we guessed it. So a metric space does not have metric cotype Q, so it doesn't satisfy this inequality up there. which is an asymptotic improvement over the trivial inequality, if and only if it does not contain arbitrarily dense, arbitrarily high dimensional L infinity grids. So you look at the m by m by m grid n times with the L infinity metric. Either all of these guys are in there, which means every finite metric space is in there, because these are universal objects. They're nets in L infinity. Or you get for free this metric cotype inequality. So this linear Moiré-Pisier theorem, through the Ribe program, became a theorem about metric spaces. And if you think a little bit, once I state this theorem, you get the cotype dichotomy theorem, which answered this question of Lovas and Aurora and others, which came from some other direction. Just this characterization, the alpha of x, it was log n to some power alpha, the alpha becomes 1 over the cotype of the space. So either a space is universal. If it's not universal, it has finite cotype, and that immediately gives you the cotype dichotomy theorem. So this is a theorem about metric spaces, but it really came from the Ribe program. It came from it took a while to find the dictionary, but once we had the dictionary and the right theorems, we can actually mimic the linear theory in the nonlinear world. So this was about universality, and now I want to show you a related issue. So we already saw dichotomy. So in the Banach space world, there are a lot of dichotomies, which are usually quite deep. One of them I will show you is a very deep fact. So this is a Bourgain-Pisier. It actually follows from what we discussed yesterday, but I will not explain how. So you give me a metric space X, and now you look at the discrete Hamming cubes. And you ask, what is the bi-Lipschitz distortion of the n-dimensional Hamming cube in X? Either it's 1 plus epsilon for every epsilon, or it grows like n to some power. So if I prove to you that the Hamming cube is inside the space with distortion log n, then it's actually there almost isometrically. There is no way to do it otherwise. So this is from the theory of nonlinear type, which we discussed yesterday. There's a finite version of this, which is local rigidity, which is, again, a phenomenon that appears a lot from Banach spaces. It's an interesting phenomenon. So the metric on the Hamming cube is indestructible in the following sense. So look at the Hamming cube. And put on, this is a set of 2 to the n points, put any metric that you want on it. But I tell you it's by Lipschitz to the original metric. It's equivalent to the Hamming metric, the L1 metric, up to a factor of 100. Okay, let's say that. Then that means that then into this metric space, I can embed an arbitrarily high dimensional cube with arbitrarily small distortion. But the initial cube, the Hamming cube. So if I take the n-dimensional cube, put any metric I want on it, but it's up to a factor 100, the original one, it remembers where it came from. Somewhere inside, there's a rescaled version, but there's a bi-Lipschitz copy with rescaling, in the sense of distortion, of an initial cube. With distortion, if it was up to factor 100, I can find inside something which is up to factor 1.0001, still a cube, provided n is large enough. So this is what the statement up there says. So you give me epsilon, and d was the 100, epsilon was the 0.001. There is a number m. It goes to infinity with n. So if the dimension is large enough, any metric on the n-dimensional cube, which is by Lipschitz with distortion d to the initial metric, has inside the m-dimensional cube. But m was going to infinity. And you can get bounds. So this is the notion of local rigidity. And using metric cotype, I can say also something about the discrete torus. There is no way, whatever metric you put in a discrete torus remembers where it came from. Okay? So, so these are things that, again, we prove using these invariants. What about binary trees? So I'll denote by Bn the complete binary tree. It's drawn here of depth n. So it has 2 to the n leaves. And the metric on it is just the shortest path metric on this graph. B infinity is just the infinite tree. This is my notation. And so this is it's not stated there, but it's just a combination of a substantial theorem of Bourgain and a very important theorem of Pisier from 1975. These are deep facts. It says the following. So this is in the Banach space world. If you give me a Banach space, X, then either the tree of depth n embeds into it with distortion 1 plus epsilon for every epsilon, or the distortion grows like log n to some power. So there is again a dichotomy. If somebody tells you you can embed trees with distortion log n, then the answer is you can embed them almost isometrically. So, and this is a deep fact. It uses, as I said, it's a combination of two substantial theorems. But you see, this is for Banach spaces. So if you have a Banach space and it contains trees, then it has the same sort of dichotomy as the cubes, as Bourgain, Millman, Wolfson proved, and as Mendel and I proved for the grids. I didn't state it. So there are many examples of these dichotomies. So if you have some sort of metric with some self-similarity, it's very often that we can show that there cannot be there's a gap between the possible distortions that these geometries can have. So motivated by this fact, that this is stated for Banach spaces, so Charlie actually asked, can we do the same thing for, so is the word you see here in red, I said a Banach space. If we really believe in the Ribe program, then this should be, if X is a metric space, then the same thing is true. Okay, that would be the natural step. Once you have a theorem of Banach spaces, you want to state the same thing for metric spaces. So Charlie asked me this. I will show you that the answer is negative, and that was a big surprise. The link to Gromov was that he actually, after we managed to prove that that the answer to this question is negative, completely coincidentally, it was being written up. Gromov mentioned to me that he proved that actually this statement is correct. So I was actually panicking, but we actually found that he proved a weaker statement. So many people noticed that this is a natural thing to look at, and here is the theorem. So the reason I want to end with this is so far I only showed you successes. So there is this program, we come up with this dictionary, boom, the theorems generalize, maybe via completely different proofs, whatever, but they generalize. This isn't something to be taken for granted. There are situations where we have a very clean statement in the Banach space world, and we have actually subtle counterexamples showing that it's not true. So in the case of trees, if you delete the word Banach space from this theorem, you can get Bn to embed into your metric space arbitrarily slowly. So you can find metric spaces such that the distortion of Bn is Sn, where Sn is any sequence for some technical reason. It has to go to infinity less than log n over log n. But you log, however you want, I can find a metric space which has this distortion exactly. And the same thing, there is no local rigidity for trees. I can find in the infinite tree, I can put on it a metric, which is by Lipschitz to the tree metric with distortion 100. But if you want to embed a binary tree into this metric, into this infinite tree with this metric, with distortion 99.99, the size of this tree is bounded. You just bound it by 100 million or some constant. And so even though it's this very nice self-similar set, you can put a new metric on it, which does not have better trees inside anywhere. So this is very different from the cube and the grids and other phenomenon. So actually, there were surprises. There were negative solutions to steps in the Ribe program before. So Bourgain's embedding theorem, so every endpoint metric space embeds with distortion log n into L2. So if x is endpoints, then x embeds to Hilbert space of distortion log 2. Bourgain actually published this was a conjecture. It was a published conjecture before of Johnson and Nishaw in which they wrote root log n. And this made sense, again, in the Ribe program, because that would be the analog of John's theorem, for those who know. So they actually specifically said, can we, as a next step, get an analog of John's theorem? And they expected it to be root log, but he proved that the answer is log, and log is the truth. So it's not quite analogous to the theory, but it's not catastrophic. It's still, instead of root log, it's log. It's still very useful. We have been studying this a lot since then. We understand in many situations how to get root log. We understand what's going on. So it existed before. I'm not saying that this was the only surprise. But this is a surprise, at least me, it kind of depressed me, because it's really qualitatively different, and it shows that there is a lot of subtleties, and the answer isn't always the answer that we want in this program. And many of the conjectures that I said could have a surprising answer. So that's it.